Hello everyone. This video will cover problem 2 of the USACO 2019 US Open Contest Silver Division, which is Cow Steeplechase 2. So this is a very difficult problem from about 2 years ago. And let's check it out. So in this problem, essentially we're given a series of line segments. There are n of them, n is up to 10 to the 5. And Farmer John wants to, well, the segments initially have like some amount of intersections. And the particular thing about these segments is that there exists one segment such that if Farmer John were to remove that segment, then there will be no intersections among the remaining segments. And so Farmer John just wants to know what is this one segment that he can remove to fix the rest, to get rid of all intersections. And if multiple segments work, he wants to remove the one with the smallest index in the input. So let's go ahead and for this example here, let's go ahead and do this sample input here. So I'm gonna go ahead and draw something. So we have the first segment is at x equal to 2, y equals 1, and it goes to 6, 1. I'm roughly eyeballing here, so these are not exact coordinates, but hopefully they are in the roughly the right place. That's segment 1. The second one is at x equal to 4, y is equal to 0, so roughly here-ish. That's roughly down here. And let's see, going to x equals 1, y is equal to 5. So like, let's eyeball this. That's like roughly about here-ish, right? Connect that. The third segment is x equal to 5, y is equal to 6. That's like about, I'm just gonna draw out here. So 5, 5, 2, 5, 6. And then the fourth segment is going to be x is equal to 2, y is equal to 7. So it's going off the screen a little bit. And then it goes to x equal to 1, y is equal to 3, down here-ish. Okay. And so in this example, if we delete this red segment right here, if we just delete this segment, I'll use a different color. If we delete this segment, then you will see that there are no intersections among the black, blue, or green segments. And so deleting the red segments works. And indeed, deleting no other segments would get rid of all intersections. If we delete the blue segments, there would still be an intersection between red and black. So in this case, the answer is the red segment was the second segment, so the answer is 2. Okay, so how can we approach this problem? Well, a naive solution, O of n squares, just iterates over all pairs of segments and then just count which segment has the most intersections. And if all these segments have either 1 or 0 intersection, they just remove the one with the lowest index among the ones that have 1 intersection. But obviously that is too slow because n is up to 10 to the 5. So let's think about a way to optimize this. And kind of the theme that we're going here is going to be line sweep. So for line sweep, usually we want to think about like maybe these like endpoints here. So I'm gonna circle I'm not gonna circle the endpoints because they're already marked, but I am going to also circle the intersections. And so now let's say we sweep from left to right in this direction. We sweep. We have a bunch of vertical lines here, one here, right? We have a bunch of like kind of like critical points or so. Actually, I'm not gonna include the intersections for now because we don't know where those are, but we do know where the endpoints are. So let's draw some places where our sweep line will stop. No, that's not an endpoint, that's an intersection, but this is an endpoint. Actually, that's the same line. It's just off kilt. That's one. There's one. And then here's one. Okay, cool. Sorry about that. Okay. Yeah, so let's take a look at this. And let's just say we maintain a set of all of these lines. line segments. And what's going to happen is we sweep from left to right. If we encounter the left endpoint, when I say left, I mean the endpoint with a smaller x value. When we meet a left endpoint, we add the segments to our set. And then when we reach the right endpoint, we remove it from the set. Now, the key observation we can note here is that at each of these intersection points, whether it's here or there, so at any given intersection point, right before the intersection occurs, if we have our set, here storing all of these segments in sorted Y order, the intersections will be next to each other. The two lines that intersect will be next to each other in the set. So let's clarify that with a bit of a difference diagram. So say we have a bunch of lines in our sets at the current moment. I'm gonna draw one here, and I'm going to draw one here. Yeah. Okay. And let's say we are currently evaluating our line sweep is currently right here. So we have 5 different segments. They are sorted. We have 5 different segments in the set, and they are sorted in Y order. Then notice that at this intersection right here, because these two segments intersect, they must have been next to each other inside. They must have been next to each other inside the set. They must be adjacent in the set when it's sorted by Y order. And let's assume that they're not adjacent, so there exists some other line in between them. Well, then that other line is inevitably going to collide with one of the lines in question, right? Or the other possibility is that the line ends early, but then once we erase this line, the two lines in question will become next to each other. So no matter what, at some point, the two line segments that intersect will be next to each other at some point in the set. Whether it's basically they're next to each other at some point in the set after one of them gets inserted or something gets erased between them. And so this gives us the following solution idea. Basically, we maintain our set. I'm going to formalize this now. We maintain I've already said this before, but I'm just going to basically like kind of restate this clearly. We have our set. We sweep from left to right. Every time we encounter the start of a segment, we're going to insert into the set, and then we're also going to check for intersection with its neighbors. And then whenever we encounter the end of a segment, we erase it or we delete it. And we also check intersection between the lines the two line segments that it was sandwiched in between. And if you want to just like think harder about this for a second, think about why this is sufficient. You can see that in each of those, if there exists some other line segment intersection that isn't counted by, there exists no other line segment intersection that isn't counted by one of these two checks, either here or there. So with I guess sandwich, the one that's sandwiched. So the one that was above and below the line segment that just got erased. Yeah, so that's going to be that. So that's how that works. Now, there's one thing to come up with a solution, but the code for this is actually quite non-trivial to implement. There are a few details we have to first figure out. The first question is, well, I was talking about sorting this these line segments by their Y value at a given X value, right? So how do we do that? It's not exactly correct to just when you insert a line segment, insert the Y of its endpoint. because then, say we have this example right here. If we insert a new line right, we have this segment right here. They have the endpoint right up there, and then say we insert a new line, say right. Say we insert a new line here, right? That's a bad example. But yeah. So say we insert a line here. I mean, and this is like where we encounter the start of it. So right here. So you can see here that if we want this line, let's label these. Let's say this is line A, this is line B, and now we're inserting line C. So if we're comparing based on the current y coordinates, then C should go in between A and B, right? However, if we instead use the y coordinates of the endpoint, then C will get erroneously placed not between A and B, but instead below B. And that is the incorrect place to place it. So we shouldn't use the y coordinate of the endpoint when we insert the line. We should instead maintain the entire line equation itself. And then each time we get to inserting a new line, we reevaluate the y coordinate that it's currently at when we're doing the comparisons. So what this looks like in code is that we would create a struct here, a struct for our line segment, and we would define a comparator. So this is all some stuff that you can look up if you're not too sure. Struct is a thing in C++. If you use a different language like Java or something, they are called classes. So it would be the comparator would be defined as the difference between the comparator will be defined as the current y value, which is different from the y value of when it was inserted. So current y value of A being less than the current y value of B means that line A goes below line B, or I'll say less than, if we consider that as below. So that's how we will sort these segments. I guess these aren't lines. These are they are line segments. Yeah, these are line segments. So that's a fine detail to deal with. The other thing to note is that we didn't really talk about how to deal with vertical lines. Vertical lines are a bit strange because vertical lines, they have two. If you ask what the current y value is, it could be any of these, right? All of these y values are valid. All of these y values can be considered the current y when we're sweeping up to this point. And so which y value do we choose? And well, the answer is that it doesn't matter which y value we choose. We can choose any arbitrary endpoint or something in between. Because let's say we pick the top endpoint, right? Well, then say it intersects with a line. Say it intersects with a line up here, then it would be able to find that line. If it's above it, it would be able to find it, except above wouldn't actually intersect with it. But now let's say that there exists a line segment that intersects. Let's say there exists a line segment that intersects with the bottom end with this line segment, this vertical one, and the bottom one is able to find it because it's right next to it in the set, but the top one can't find it because the top one has some other line in between that's blocking it. Well, then we can just use this line instead as the intersection. So you can see here that it doesn't really matter which y value we choose for vertical lines. It will always be able to find at least one. If there exists an intersecting segment, then we will always be able to find one next to one of the two endpoints or anything in between. So that's how vertical lines are dealt with. The final thing I want to talk about is how do we actually check line intersection. So now one way you can think about doing line intersections, maybe what you learned in school, right? Like the y equals mx plus b equation. You have y1 equals mx. Let's say you have segments A and segments B all use the same notation. So we have y. Actually, yeah, we have MA and we have MA and MB and BA. And then we have our second line. And then you would just solve this like equation right here. You would solve for you would solve for what value of x they intersect at, get the corresponding y, and then you want to check, and then you just check if the point you find is actually like on the line segment and not just like going on actually on the line segment. Because like maybe you have this line here, but the infinite extending line goes further. If you pick like this point isn't actually on the line segment. It's only on the line. So then you can just do a simple check of like, is it between the x's and is it between the y's? After you find the points that the two lines intersect at. So that is one way of doing line intersection. However, the problem with that is that, well, first off, when you calculate a slope, slope is like rise over run, right? It's like y2, it's like, yeah, it's like y, the y's over the x's. So then like if you have a vertical line doesn't have a defined slope. So you have to like do a special case for vertical line intersections. The second issue is that you have to use doubles because your slope could be a decimal value. And the thing about doubles is that in programming, you often want to avoid doubles whenever possible because doubles can introduce precision errors. So without going into too much detail on like how precision errors work, and you can Google this if you are interested. Basically, in coding, in programming, your numbers don't. Let's say you have like 1/3, right? We know that 1/3 is equal to 0.333 repeating. So, or in other words, it's equal to like 0.3 bar, right? However, a computer can't like actually store an infinite number of threes. So instead, it just stores up to like enough decimal points. I think like double does like roughly 14 decimal points or so, 14 or 15, I don't quite remember. So then it will store something like 3333, and then it'll truncate it off at the very end. And so that doesn't seem like a big deal because like 14 decimal points sounds like a lot. But then when you start doing like division and you start doing like division, you end up needing like a lot more precision, and then you can like lose a lot of. Essentially, when you do a lot of computation with doubles, you can lose a lot of the precision along the way, and 14 decimal points might end up not being sufficient. And so when the precision errors are especially risky for something like line intersection, because like let's say you have a segment here and you have a segment there. So this is a very close point. So then maybe like, so your program needs to be able to tell the difference between like this and like just barely touching but not actually touching. The program needs to be able to tell the difference between actually touching and not touching. And if the boundaries are very like small, it only like then like a small precision error can go a huge way in like messing up your calculations and having it determine that it intersects when it actually doesn't, or vice versa. And so that's why you generally want to avoid doubles whenever possible. And there is a way to do line segment intersection without using doubles at all, although it's a bit more it's not something that like you learn like elementary or middle school. It's like you can use like vectors and cross products. And so I don't want to get too much into like how that is done because you can like look that stuff up, or you can just wait until you learn it in school. But I do include it in my code simply because, and that's also what the editorial code uses, simply because I want to maintain my precision and get the correct answer and not risk getting the wrong answer. And so I have that stuff in my code that I will show later. Okay, so with all of the exceptions out of the way, let's go actually look at the code. So normally I would do a live coding session, but like this code actually took me a non-trivial amount of time to write. And if I wrote the code live as well, then this video will be like an hour long, and I don't want to do that. So I've already written the code ahead of time. Let's just go through this code and see what it does. And I will be skipping over details a little bit because some of the stuff is just like more stuff that you like have to Google or like figure out. But this code will be in the GitHub repository linked in the description if you want to check it out in more depth. Okay, so here we have, so actually before I jump into the main program, I'm gonna look up here at this stuff. So I first define a bunch of different like structs and functions that will help me solve the problem. So first I define a struct for a point. So a point is simply defined as an X and a Y. That's pretty easy. And I'm using a long simply because values go up to 10 to the the values get pretty huge in this problem. They're already up to 10 to the 9 when you input them in, and when you do like multiplication with them, they can overflow integer or 32-bit integers. So I use 64-bit integers by default. So we have point. I have a method for vec, which is just taking a difference between the points, and that's needed for all the fancy like cross product stuff I'm doing in order to compute the line segment intersection stuff. So this is all kind of just like some library code that like I don't want to get too much into. I do put like more in-depth like comments here explaining what they mean if you want to look at the code later. I have my current x. So this current x is going to be a global variable, and that's because I reference current x inside my comparator when I'm comparing the two segments in the set. And so I make this a global variable so that my comparator can access the variable. Now onto the actual segment struct or segment class. So this is going to define a line segment, which is between 2 points A and B. I also keep track of the index of these segments because I need to print the index at the very end for the answer. Now I have here, this is the comparator. So in C++, in order to define a comparator between structs, you simply need to define what it means for one thing to be less than another. So in this case, I'm defining what it means for one segment to be less than the other segment. And by less, I mean below in the set. So this is like some special case stuff for dealing with vertical lines. But the point being is that I basically have like the current y value is defined as like we have like the slope times like this stuff plus like a y-intercept kind of, but like it's slightly different because I factored it. And you can just do out the math and like confirm that all this stuff does agree with the math and it does all work out. And one caveat is I do use 128-bit integers here simply because when I multiply these values together, the numbers can get very large. They can get up to 10 to the 27. So even 64-bit integers or long longs are not enough. So I use 128 here. The editorial or like the solution code that USACO provides, they use doubles here to deal with this. But like as I said before, I prefer not to use doubles when possible. The doubles do end up working for this problem, I guess, because the test cases aren't that precise. But in general, I don't think it's good practice to use doubles if it's not necessary. So I don't want to get too much into this. This is just like you set up you solve for this and you just like multiply the stuff both sides by like the denominator to get rid of the doubles. Yeah. And then here we have intersection. So again, this is just like the cross product stuff I was talking about earlier. I linked also an article here that explains the stuff if you want to read that. And now let's get to the actual program. Okay, now that we got all the geometry and math stuff out of the way, let's actually do the line sweep part. So we read in the input. We have all our different coordinates, and then I push them into like a set. So this is going to be my set of endpoints. So I have my left endpoint and my right endpoint. And the important thing here is that when I push them when I sort the endpoints, I explicitly define I explicitly do this trick here of adding n to the index of all the right endpoints. First, because this lets me distinguish between left and right endpoints, because if the index is less than n, I know it's a left endpoint. If it's greater than or equal to n, I know it's a right endpoint. But second is because for the same x value, these values will be smaller than these values. And so therefore, it'll be sorted such that all the insertions happen before all the deletions. And so that makes a difference because if I sort like willy-nilly, right? Like let's do an example here. Let's say I have a line here and I have another line here. Or vertical line is a bad example. That's fine, actually. I'll do vertical line. Yeah, let's say I have this example here and I have these endpoints and these endpoints. If I first insert this, then erase that, then this segment won't be able to find the segment that it intersects with when I insert it. So I need to process these endpoints. I need to first insert the other line, or I need to first insert the line before I then process the erase. All right, so I insert all the endpoints, I sort them. Ret A and ret B are just going to be, I store the answer. So what happens is basically I stop the algorithm the moment I find an intersection, and then I record the two indices that I found, and then at the very end I check which one of these indices is the one that I need to remove and print as the answer. I have my set of segments. Let's see. I iterate. Oh, this is just a yeah, okay, yeah, I see now. Okay. And I don't want to get to, okay, so basically the high level here is that I have my two cases. Remember, I is greater than or equal to n. So I have delete a segment from the set. So therefore I just erase the segment and I check if the two segments on both sides of the deleted one inside the set intersect. And then similar, the other case, when I insert a segment, I simply check on the two end on like above and below it. I check the two neighboring segments and I see if I intersect with them. And if I do intersect, I stop the out. And anytime I find an intersection, I set them equal to ret A and B, and I immediately terminate. And at the very end, I simply print whichever one has a higher count. So by default, I assume that ret A is the answer, and then I check if ret B has a greater count. And ret A is always the minimum of the two, so it will always be the smaller one, which is good because the problem wants to print the smaller index. And yeah, that is the code for this. It took me quite a while to write and also quite a while to debug. So this was quite the problem. So yeah, that's going to be it. So thank you for watching.